Hey there, this is Arnav from Pebble, and welcome back to the Linear Algebra Introductory Series. In the last video, we talked about inverses, how we can use those in our very popular method of finding the solutions to simultaneous linear systems. And in this video, I wanted to talk about LU decompositions, which are another very popular way to do the exact same thing. And it really just depends on which one is. This is another method to do the same thing, so it just depends on which is more efficient, but I want to give you the options so that you know the different ways to do it. Okay, so what is an LU decomposition? What do the L and U stand for in that? Well, an LU decomposition is basically two matrices that when multiplied together equal our original matrix A. Okay? And L in this case is going to be lower triangular, and U in this case is going to be upper triangular. And a refresher as to what those mean: lower triangular is everything above the diagonal is 0, and upper triangular is everything below the diagonal is 0. And so once we get the lower end, so the LU decomposition of a matrix is a lower triangular matrix multiply an upper triangular matrix that equal the original matrix. And that's how we're going to define it. And so to decompose A into the LU decomposition form, I want you to take this part as face value as we did with inverses. We need to transform A into an upper triangular matrix solely by using the third elementary row operation. Okay, and we kind of just, this is like doing the row reduced form transformations, but we just have to use only the third elementary row operation. Okay, and for a refresher of what the third elementary row operation is, that's when you add a multiple of another row to the row. And so we have to do that. So let's take a look at this matrix. 2, minus 1, 3, 4, 2, 1, minus 6, minus 1, 2. This 3 by 3 matrix. So in order to find the LU decomposition, let's first transform this into upper triangular. Okay, so we're going to add the second row. But with -2 times the first row to get rid of this 4. And then we're going to get rid of this -6 by adding to the third row 3 times the first row. And then we're going to get rid of this 1, -1 by adding to the third row 1 times the second row. Okay? And so what will that look like at the end? Well, that will look like 2 minus 1, 3, 0, 4, minus 5, and 0, 0, 6. And so this, as you can see, is upper triangular. And so if square matrix A can be reduced into an upper triangular matrix by using only the third type, then that means we can find the LU decomposition. And that also means that there is some sequence of elementary matrices, like we did here by getting rid of this 4, getting rid of this -6, and getting rid of this -1, that when multiplied by our original matrix gives us U. So I'm going to denote that as the E is like the cumulative form of all the elementary matrices that we did, and then that times A is going to be equal to U. Okay? And so let's isolate A in this just by using the inverse. So A equals E inverse U. Okay? And I just multiplied E inverse to both sides, putting it first, and then these two, the E's would cancel, and we would get an E on the right side. So the inverse of the cumulative elementary matrices that we do to A to get U is going to be what we multiply by U to get A, obviously, which I just said the same thing twice in two different words. And this looks very familiar to this form that we have up here, so it's logical to say that inverse of the cumulative is going to equal L. And so that's how we define the lower triangular matrix in our LU decomposition. We take all the elementary matrices that we did to get U. Okay, we find the inverses of all of them, and then we multiply them together, and that's going to give us L. Okay? And this follows a very similar logic to inverses, just because we're doing what we did is the opposite. In inverses, we just looked at the matrix transformed into the identity, and then we saw how those elementary row operations were reflected in the identity, and when those two multiplied, we got the identity back. And so we're doing the same thing here, just this will turn into a different, this will not be the inverse, rather it's the lower triangular matrix in this case. And so let's actually find L for this example here. So this is U, right? It's our upper triangular. And this is, just make sure this is abundantly clear that this is A. And so what were our operations? Well, they were, this first one was get rid of the 4 that was on the second row. So that was our matrix for that. That corresponds to the operation. And then we also had 1, 0, 0, 0, 1, 0, and then minus 3, 0, 1. And that got rid of the minus 6. And then we also had one, the final one, that got rid of the minus 1, which was this one. And one thing to note here is they're all lower triangular, and that's the reason why we can only use the third operation, because we will be getting a lower triangular with this one. That's just very, very important in finding LU decompositions that we have to do this. So that's why we only use the third one. And so taking the inverse of all of these, I'm not going to rewrite it, but the inverse of it is just, these two will stay the same actually, and then this one, the 2 just becomes positive. And you can prove this. You can go and find the inverse for yourself. I'm not going to do it just for the sake of time, but you can definitely go out and try it. And so what this means is that E, the cumulative inverse, is just going to equal all of these matrices multiplied together. All of these matrices multiplied together. So 1, 0, 0, 0, 1, 0, minus 3, 0, 1. And then multiplied by the final one, 1, 0, 0, 0, 1, 0, 0, minus 1, 1. So when we multiply all these together, we should get our cumulative matrix here, which is also L. And so once you do that multiplication out, you'll get 1, 0, 0, 2, 1, 0, minus 3, minus 1, 1. And this is just going to equal L. Okay? So what we came to here is to say that 2 minus 1, 3, or 2, 1, minus 6, minus 1, 2, which was A, by the way. So this is A. That equals 1, 0, 0, 2, 1, 0, minus 3, minus 1, 1, multiplied with 2 minus 1, 3, 0, 4, minus 5, 0, 0, 6, which was our upper. This is lower, this is upper. Okay? And this is all sort of, you know, I want you to actually, this is just all sort of works out, but I also want you to just practice this multiplication here, multiply it out, just so you actually confirm this for yourself, right? Because I told you to just take this at face value, but once you do this multiplication, you'll see that it's not just face value. There's a lot of it actually makes sense when you do it this way, when you convert it like this, just because of how operations are defined in the matrix world. When we do an operation like this, we can see how we're sort of just working backwards from matrix to the identity matrix, and that's just the main core to work like this, like the inverse in LU decomposition. Okay, so as a summary of the decomposition process, use only the third elementary row operation to take a square matrix A, make it upper triangular, and then if it's not possible to do this, then you're done. You can't find the LU decomposition. But if you can, then the end upper triangle matrix is going to be a U, and then you're going to take the inverse of all the operations that you did as in matrix form, multiply them together, and that's going to be your lower triangular matrix. Okay, so we're not going to do another example in this video, but there are problems online that you definitely should try. And we're actually going to go into how do we solve systems of simultaneous linear equations using LU decomposition, because right now, when I was learning this at least, I was like, there's no way you can use this to solve a system. I don't see it, but there is definitely a way. Okay, so let's revisit our definition of a linear system in terms of matrix multiplication and a matrix equation. AX equals B, okay? But we know that A is equal to LU, so LUX equals B. Let's associate U and X here. Well, okay. Either way, either one of these, they don't make sense. How would you use this to solve B? It just looks like you added another matrix, which makes it a lot more painful to solve. But what this does is it simplifies the process quite a bit, because, well, UX in itself is another system, right? UX, it's variables times your matrix, times the matrix. So this is going to be another solution like B. So we're just going to call this Y, right? And so L times Y equals B. So we know what B is, we know what L is, so we can find Y. And then once we find Y, we know what U is, so we can find X like that. And that's basically just the main logic behind using LU decomposition to find solutions to systems of simultaneous linear equations. So let's take our same matrix, and 2 minus 1, 3, 4, 2, 1, A by the way, 6 minus 1, 2, and then multiply that by our three variables, x, y, and z, and then that's going to equal a solution 9, 9, 12. Okay, so we can use our LU decomposition here. So let's first take the lower, and let's do this Ly equals B step. So 1, 0, 0, 2, 1, 0, minus 3, minus 1, 1. And you can see how we can already find out what one of the variables is, and then from that it's easy to find the second variable and third, because they're already in this form where it's already in reduced form. This is like flipped, but it's already in a reduced-ish form, and so there's really no massive computation that has to be done. And so this times another set of variables like j, k, jkm, that's going to equal b, so 9, 9, 9, 9, 12. And so if you were to solve for jkm, you would get that j equals 9, k equals minus 9, and m equals 30. And so the way you just, and the way I did this, just so it's abundantly clear, is that, well, 1j equals 9, and then 2j plus 1k equals 9. So 2 of 9, which is 18, plus k equals 9, so k has to be equal to minus 9, and then the same thing here. So you just easily have one variable given to you, and we all know how to solve systems of linear equations just by that. Just by being given one variable easily, and everything else is just nicely there for you. Okay, so now ux equals y. So we found y, which is 9 minus 9, 30. So we found y here. So the next thing to do is our upper triangular matrix, which was 2 minus 1, 3, 0, 4, minus 5, and 0, 0, 6. This times our original variables x, y, and z equals the new matrix that we found using the LU decomposition. And so when we solve this, we're going to get that x equals minus 1, y equals 4, z equals 5. And so that's your answer. That's pretty much it. And this is very simple because you get from here 6z equals 30, and then minus 5z plus 4y equals minus 9. So you just plug in the z that you know, and then you get y easily from there. And it's really just, it's just really simple to compute everything from there. Okay, so LU decompositions are another way to find a solution, and it really just depends on which one you're more comfortable with and which one is more effective in the situation that you're in. So if you notice, or if they give you like the upper triangular for for a matrix, then it might be smarter to go with LU decomposition. Or if they don't, maybe you'd want to do something else. It's really just up to you, but this is another option that you have when solving systems of linear equations. And so with that, that concludes section 1 of linear algebra. This is the fourth video, and that is everything in the basics of matrices and systems of linear equations. And so in the next video, we'll move on to section 2, which will start getting into vectors and vector spaces, which is very, very interesting and also a huge chunk of linear algebra and very important to understand. Okay, see you then.